So for the last part, we'll look at the so-called reduction formulae. And what that refers to is basically situations where you use integration by parts, but instead of getting a function for the integral and solving it in one go, what you get is something less. You get a formula that relates the integral to a simpler integral that looks more or less the same. So let's look at an example to see what we mean by that. So for the example, we'll define an integral I sub n. So it depends on a parameter n as x to the power n times e to the minus x dx. This is also a very famous integral that you will see in physics and also in probability theory. And so here, just to make it clear, this n is a natural number. 0, 1, 2, 3, and so on. So what we can do with integration by parts is we can use what we already know. We can call this u, and we can call this v prime. So maybe to make it explicit, for u, you always want to choose something that's easy to differentiate, and a polynomial definitely is easy to differentiate. And for v prime, you want to take something that's easy to integrate, and e to the minus x, that's easy to integrate. You will get e to the minus x with a minus sign. So if u is x to the n, then u prime is n times x to the n minus 1, and if v prime is e to the minus x, then v is minus e to the minus x. And so that integration by parts gives us u times v, so x to the n e to the minus x, and then a minus, and then plus u prime, so n times x to the n minus 1, and actually let me take out the signs. So this is u prime, and then v is minus e to the minus x dx. So this is v. And so now we can clean that up a bit to write x to the n e to the minus x plus n times x to the n minus 1 e to the minus x dx. And now if you look at the form of the integral that you have on the right hand side here, it looks exactly like what we started from, except the exponent is n minus 1, and in the beginning it was n. So we managed to lower the exponent by 1. And so what we can do is we can write this integral, this is just I sub n minus 1, and from that I basically get that my in, the thing that I started from, is minus x to the power n e to the minus x plus n times I minus 1. So this is an example of a reduction formula, because it gives us not the integral itself, but the integral expressed as a simpler integral. And then if you want to know what I n minus 1 is, we can write it as I n minus 2, and so on. So let's use that formula to calculate what I n is for various values of n. So in order to do that, we will start with I0. And for I0, we can calculate that directly. That's x to the power 0 e to the minus x dx. X to the 0, that is 1. So here we have integral of e to the minus x dx. And that's minus e to the minus x plus a constant. So then I1 we can use with our formula. So I1 is minus x to the power 1 e to the minus x plus 1 times I0, and we just calculated what I0 is. So we get minus x dx plus minus e to the minus x plus constant. And we can factor out the minus and the e to the minus x to get x plus 1, like this. And now you can keep building up expressions for the higher order i's. So I2, for instance, is minus x squared e to the minus x plus 2 times I1. So that's minus x squared e to the minus x plus, or rather, minus 2 times e to the minus x, x plus 1, plus a constant. And now we can again factor out minus e to the minus x, x squared plus 2x plus 2. And we still have our constant. And like this, you can keep going. You can try to build up a general prescription for what IN is, but that might be a bit complex. But the upshot is that basically the reduction formula gives you your answer, but not directly. It tells you how to compute the answer from a simpler integral. So for the second example, we'll look at an expression I sub n, which is the integral 0 to pi over 2 of cosine to the power nx dx. So in order to apply integration by parts, we'll first rewrite this as cosine to the power n minus 1x cosine x dx, and then we'll call this thing u and this thing v prime. So you always want to choose something that you can easily differentiate for u and something that you can easily integrate for v prime. So with those choices, we have that u is cosine n minus 1 and u prime is n minus 1 cosine n minus 2x, and then derivative of cosine, that's a sine with a minus. V prime is cosine of x, and therefore v is sine of x. So what does that give us for integration by parts? We get u times v sine x. And here we have to be a bit careful. We're looking at a definite integral, so we have to evaluate what this thing is at pi over 2 and 0. And then minus, and it's going to be u prime times v, so I'm going to take out the n minus 1 from the integral. I'm going to change the minus to a plus, because it's minus here as well. And then I'm going to write n minus 2x sine x, and then times another sine x from v. And here it's 0 to pi over 2. And so in other words, this whole thing, including the sine, that comes from u prime, and this thing right here, that's v. So now we can actually calculate what that is. So if you substitute x is pi over 2, cosine is going to become 0. And if you substitute x is 0 for the lower bound, sine is going to become 0. So this term vanishes because of the bounds. And we're left with n minus 1 times integral pi over 2 cosine n minus 2 x sine squared x dx. So now the next step is we have that sine squared. Let's rewrite that in function of cosine again, and let's write it as 1 minus cosine squared. And so now to continue, what I'll do is I'll split that up, the integral, and I get an integral cosine n minus 2x dx plus minus n minus 1 integral pi over 2 cosine n x dx. So here I had an n minus 2, and then I had a squared, and n minus 2 plus 2 gives me my cosine n here. And so now you see that this thing is I n minus 2, and this thing is I n again, and therefore what I've derived is that I n is equal to n minus 1 times n minus 2, I n minus 2, minus n minus 1 I n. I can bring the I n's all to the same side, so I get plus n minus 1 I n is equal to n minus 1 I n minus 2. So n times I n is n minus 1 I n minus 2, and therefore I n is n minus 1 divided by n I n minus 2. This reduction formula doesn't tell you something about I n in function of I n minus 1. It gives you something that skips 1 and gives you the answer in function of I n minus 2. So let's calculate a few concrete values. So for I0, we have integral of cosine to the power 0 x dx, and that's pi over 2. And for I1, we have integral of cosine, so that's sine x pi over 2 0, and so that's sine of pi over 2 or 1. For n arbitrary, we have to distinguish between two cases because you can already see a difference 0 and 1 here. So for n even, what we get for in is that it's n minus 1 over n times in minus 2. What is in minus 2? Well, it's n minus 3 divided by n minus 2 times in minus 4. And that's it's n minus 5 divided by n minus 4. And what you end up seeing is that you go down in steps of 2, and since n is even, you get odd numbers in the numerator and even numbers in the denominator. And you keep doing that until you reach n 4 to 0. So you end up with 5 times 3 times 1 divided by 6 times 4 times 2. And then here you now end up at I0, and that gives you an extra factor of pi over 2. So that's the case for n even. For n odd, the principle is the same, but the result is a bit different. So the formula starts off the same way, n minus 3, n minus 2, and so on. And then, so n is odd. You subtract odd numbers for the numerator, so that gives you even numbers. And then when n gets less and less, you end up with 4 times 2, and then divided by 1 plus that number, so it's 5 times 3, and then times I1, that's where it ends, and that's just 1. So you see actually quite different answer. One has a pi in it, the other one doesn't, for a expression that looked very similar to the beginning.